All right, welcome back, everybody. You might remember in the past we studied partial derivatives. So for example, if we had f of xy equals x squared y, my partial derivative with respect to x would be 2xy. The idea behind it was we did the derivative with respect to x, therefore we held y constant. And if you need more detail on the session on partial derivatives, you're always welcome to go back to the previous video. Just like we did the derivative, the partial derivative with one of these, we can also integrate this in a very similar way. So for example, if I wanted to integrate 2xy with respect to x, right? My 2y would be a constant, and I would simply be integrating x dx. If I integrate x dx, so I have 2y as my constant, x squared over 2, and when I simplify, I get x squared y, and then of course we need some sort of a constant, which potentially could be a function of y. Now this constant is not the subject of today's lesson. We'll talk about that in a future section. All right, but the idea that we can go backwards and reconstitute our function is what we're going to talk about. So I can, let's do a very basic example. I'm going to do an integral from 1 to x of 2x squared y to the negative 2 power plus 2y with respect to y, which means that I'm going to use the same idea as my partial derivatives. I'm going to hold x constant and only integrate with respect to y. So why don't you pause the video, why don't you think through the integral, and we'll talk about it on the back end. All right, I hope you thought about it. I wound up with negative 2x squared over y plus y squared from 1 to x. I then plugged in my bounds, so I get negative 2x squared over x plus x squared minus negative 2x squared over 1, because I'm plugging in my lower bound now, plus 1. And hopefully you did the algebra. If you didn't, pause it now. If you did, my final answer would be 3x squared minus 2x minus 1. Now that was just a single integral on a multivariate function. Here we're going to do what we call an iterated integral, which we will be integrating with respect to x and then with respect to y, or vice versa. The key with these iterated integrals is the setup, and that's where I'm going to spend most of my time. If you're watching this video, you've already done integration, so I'm going to expect that you can do that on your own. All right. So a double integral measures volume under a surface bounded by a region. Now, if you're not given a surface and you're just given a region, you are measuring the area in the plane bounded by the region. All right. As I said, the order of integration is either going to be dy dx or dx dy. All right. The order in general doesn't matter. You're going to get the same answer either way. I would suggest you do whatever makes the first integral easier. That's going to be the key to success. All right. So over the course of this video, we're going to do a few examples, and I'm going to pass along just some helpful hints that may make doing iterated integrals just a little bit easier. All right, so let's try our first example. All right, use an iterated integral to find the area of the region bounded by the graphs f of x equals sine x, g of x equals cosine x, between pi over 4 and 5 pi over 4. Now, anytime you're setting up one of these, we definitely have to make a graph. All right, for me, in general, it's just much, much easier to see if we create a graph. Now, your graph only needs to be a sketch, but the sketch is going to give you a really good idea of what is to come. So pi over 2, pi, 3 pi over 2, 2 pi. Now I left a lot of space because I need to put in pi over 4, and I need to put in 5 pi over 4. All right, so let's start with the graph of sine. Graph of sine starts here and goes up, and then it goes through pi. And again, you're seeing that I am not necessarily the greatest graph drawer, but I'm going to try my best. There we go. Not too bad on the whole. All right, and cosine is going to come down. Like that. Kind of, sort of. All right, let's see. And these two graphs intersect at pi over 4 and 5 pi over 4. So, all right, so it looks like pi over 4 and 5 pi over 4 certainly can be some starting bounds of integration. Now, they are across the x-axis. So I would suggest that x is going to be those are my bounds for integration. Now, the y bounds are a little bit harder, all right? All right, so let me change colors here. All right, because now we have to look at the graph. After pi over 4, which is the larger graph? The larger graph is sine. So that's going to be my upper bound, all right? So for y, and of course, my lower bound is the graph that's beneath it, which would be cosine x. So the graph is really helpful in getting your bounds for integration. All right, so now we've got to set this up. I'm going to change colors just for a little contrast. And we set it up by saying x equals pi over 4. X equals 5 pi over 4, y equals cosine x is my lower bound, y equals sine x is my upper bound. Now we don't have a surface, so we're simply integrating across the plane. Now you may ask why I'm integrating with respect to y first. Well, if you notice, my bounds for y are functions. My bounds for x are constants. I want to do my constants last because if I'm looking for area, I'd really love it to be a number in the end, correct? So that would be one of the judgments I would make, is that if you have one set of bounds that are functions, another set of bounds that are constants, I would do the constants last. So basically what we're going to do is this. We are going to integrate from the inside out. So that's the first integral we're doing. All right. So if we're integrating dy, we simply get y, which is really great. So I'm going to do got to rewrite everything. X equals pi over 4. X equals 5 pi over 4. And when we integrate, we get y. Cosine x to sine x. And then my dx is out here waiting for later. So why don't you pause the video right now, input your upper and lower bound, and then let's set up for our second integral. All right, hopefully you did it correctly. Let's take a look. So x equals pi over 4, x equals 5 pi over 4. If I'm plugging in my upper bound of sine x, I subtract my lower bound of cosine x, and I have my dx right here. So one thing to check is that after your first integral is done, whatever your variable was, whatever you integrated with respect to, that letter's got to be gone. So for example, we integrated with respect to y. So at this point, we should have no y's left. All right, and that's what we have. But now we have a single variable integral, just like we had way back when we were doing Calc 1. So why don't you pause the video now? Why don't you execute this integral, and we'll talk about it on the back end. All right, so let's take a look. If I integrate sine x, I get negative cosine x. If I integrate cosine x, I get sine x, so minus sine x, from pi over 4 to 5 pi over 4. And when I plug in those bounds, I get a final answer of 2 radical 2. And you could even say is the area bounded by the region. Sounds good. All right. So in our next example, we're going to add in a surface. All right. So let's prep for that. Here's our next example. Looks just a little bit different. All right. I have a double integral. R means over a region. All right. Now I have a function here. This function, f of xy, is your surface. So this is the surface. So once we see that we have a surface, which is essentially our height, and we're multiplying our height times our area, we then have a volume. All right. So now the question is, what order do we integrate in? Well, I look over at my region and I see that I'm integrating across the x-axis between 0 and 1. I'm integrating across the y-axis between -1 and 2. So being that I have constants on both, you're able to pick which one you want to do. And you don't necessarily need to pick the exact same one that I do. You should be getting the same answer. All right, so I'm going to set it up the way I think it should be, which is I'm going to integrate across the x first. I like zeros. Zeros make for nice plugins. So I want to do that first. So I'm going to integrate. So y equals -1, y equals 2, x equals 0, x equals 1. And I just looked that way because my x plus y squared is really just kind of a power rule for integration. So there's no advantage either way. So like I said, after I do my first integral, plugging in a 0 looks really nice to me. So that's why I picked this order. So why don't you pause the video now and do that first integral, and then we'll check our work. All right, so when we do our first integral, let me rewrite. By integrating with respect to x, All right, so x, I raise it by 1 and divide by the new exponent. So I have 1/2 x squared. Now I'm going to add y squared is a constant. So when I integrate y squared, it's going to be y squared times x between x equals 0 and x equals 1. And I have my dy on the outside. Now, if you at this point wanted to check your work, all right, you could take this function and you can do your partial derivative with respect to x. All right. If you wound up with that function, you would be fine. We're fairly confident that we're doing okay, so we're just going to move forward. All right. So now I need to plug in my limits. And when I plugged in my limits, I'm going to have to rewrite. So y equals -1, y equals 2. I get 1/2 plus y squared dy. And now we are once again back to that Calc 1 type integral. So why don't you pause the video at this point, and why don't you finish it up for me, and we'll talk about the answer on the back end. All right, so if you successfully finish this up, if I integrate 1/2, I get 1/2 y, and you integrate y squared, I get 1/3 y cubed between -1 and 2. And when you plug in the limits and do a little bit of algebra, you are going to get an answer of 9/2. All right, so like I said, a good setup that suits you is actually going to make things a whole lot easier. All right, so I would like to do one more example. Just take it maybe just to the next level. And of course, there'll be plenty more that you need to do for practice, but this one is kind of interesting. 1/1 plus xy, all right? And that's a terrible r. I'm going to make a better r out of that. All right, my region is going to be from 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 1. So I now have x and y both being constants. So realistically, you say, I can do either one first. And that's fine. However, what I do have now is I do have a surface I want to look at. And this surface is not a power rule either way. All right, so let's think about it. If you wanted to integrate with respect to x, excuse me 1 second. Sorry about that. This should be an x up here, not a 1. All right, so if I wanted to integrate with respect to x, what would be the technique you would use? And you have an x in the top and an x in the bottom. So is there a technique to do like a quotient rule for integrals? You say, yeah, there is. It's integration by partial fraction, but for that we need powers and it's kind of hard. It takes a long time and I don't really want to explore it. All right. So now you say, well, if I integrated with respect to y, what would be my technique? Well, I thought about that and I said, if I integrated with respect to y, then I would need to do a u substitution, which I consider much, much easier than any sort of partial fraction. All right, so I'm going to make u equal to 1 plus xy, or the bottom of my function, or my surface. And then du would be x dy. All right, so, and even before I write out the integral, I'm going to change my limits. So my y equals 0. I'm going to take 0 and I'm going to plug it into my u function. And I'm going to get u equals 1. I'm going to take my y equals 1. I'm going to plug it into my u function, and I get u equals 1 plus x. So now when I write my integral, I'm not going to write y limits because I'm using u instead. I'm going to write u limits. So x equals 0, x equals 1, u equals 1, u equals 1 plus x. And now I'm going to look back at my surface, and I'm going to make my substitutions. All right, and what my substitutions basically tell me is I have du over u with a little dx out here. And I'm going to do my inside integral first. All right, so why don't you pause the video at this point and knock out that inside integral for me. All right, so I'm going to rewrite x equals 0, x equals 1. Got to keep this stuff coming down. If I integrate du over u, I get natural log of u between 1 and 1 plus x with a dx out here. All right, and now I need to plug in my limits. So I have the integral from x equals 0 to x equals 1. And I'm going to plug in ln of 1 plus x minus the ln of 1. All right, and I know that the ln of 1 is 0, so I'm left with the integral of x equals 0, x equals 1, ln 1 plus x dx. And as I said in the past, however way you do this integral is up to you. I've done plenty of ln integrals that I know that the answer is 1 plus x ln 1 plus x minus 1 plus x, just like that, between 0 and 1. All right, and now I'm going to plug in my limits. So why don't you pause the video now, plug in those limits, work it down, and we'll talk about the answer. All righty. So at this point, you hopefully plugged in your limits, and I got 2 ln 2 minus 1. Now you can always use your power property of logarithms, which basically takes that 2 and you can bring it up as the power. So I can say my final answer would be the ln of 2 squared, which is 4 minus 1. So that is my best answer. All right. That is just a couple of beginning examples with iterated integrals. I would definitely recommend practicing more. There's a variety of different integrals you can always get more experience with, but this should help you get started. Thanks for listening. Talk to you soon.